Okay, welcome you all. First, I would like to thank him and other organizers for organizing such a nice event so that we can all come together and listen to each other. Uh, I have been asked to give lectures on global 21 centimeter signal theory, and so before I go into the details, I would like to give you an overview just to set the stage. Uh, Most of you already know about that. Uh, for you, that it will be just a refreshing kind of thing, and then slowly I will go into the theory of part of the global signal. So let's start with this very familiar picture. Uh, so this shows how our universe evolved through cosmic time. Our universe started with the Big Bang, and then during the recombination epoch, proton and electron combined to form neutral hydrogen, and that happened around redshift 1100. After that, universe became mostly neutral with 75% in weight is in the form of hydrogen and 24% in weight is in the form of helium. That's composes mostly the baryon part, and then you have dark matter, dark energy. And then at that time, there are no sources, as you know, no luminous sources, and universe was basically dark during that phase, and that episode is known as Dark Ages. And it is believed that at around 25 or 30, first luminous sources that were formed in the universe, and radiation from that sources, UV radiation, and then X-ray radiation, all kinds of radiation, they started to change the first thermal state of the universe. So basically, they changed the spin temperature, IGM temperature, and that epoch is known as cosmic dawn. And later, when more and more UV radiation actually from the source, those sources started to ionize the neutral hydrogen around them, like that. We expect to have ionized regions around those sources, and later more and more ionized sources were formed, and then eventually they overlapped with each other, and that process of ionization of neutral hydrogen is known as the epoch of reionization. And at around redshift 6, almost 99% of neutral hydrogen got ionized. And after that, so epoch after the redshift 6 is known as the post-reionized epoch. So this is the interest of our interest. So we study the epoch of reionization cosmic dawn, and there are several probes, and we are interested in the in observing this epoch using global using 21 centimeter signal. Okay. So starting from the very beginning. So as I said, that universe was full of neutral hydrogen, So here I show these energy levels of neutral hydrogen atoms. You are already familiar with this. So these are different transitions: Lyman alpha series, Balmer series, Paschen series, and then if we focus on the ground state, so mostly almost all neutral hydrogen in our universe is in the ground state because temperature is very low. So you will find them in the ground state. Okay. So how this 21st century signal is originated? Uh, see, uh, if we focus on this down state, this it has orbital angular momentum that is 0. But since electron and both are spin, so the total angular momentum is the sum of electron and proton spin. So that is F equal to S plus I. S is the electron spin, I is the spin, and both are half. Okay. Now what happens that um, uh, magnetic moment of proton have magnetic moment, and they produces magnetic field outside it, right? And electron is also a charged particle. So electron magnetic moment experiences that magnetic field. So proton is producing magnetic field, and the electron is experiencing that magnetic field. So there will be interaction between proton magnetic moment and electron magnetic moment, and that will cause energy correction to the ground state hydrogen ground state energy level of hydrogen atom. This interaction between proton magnetic moment and electromagnetic moment, and the energy correction uh, can be written in this form. So there are some steps before that, before we can actually write that. So correction to the ground state energy is EHF, and this is called hyperfine splitting. The interaction between photon magnetic moment and electron magnetic moment is called hyperfine splitting, and you might have already studied it. So these are all constants, and then just look at this term, this S dot I. So this is the interaction term between proton magnetic moment and electron magnetic moment. Okay, now if I write S dot I, that is the spin of electron and spin of proton, that can be written in terms of this. So it can be written in terms of F square operator minus S square operator minus I square operator, and these are the eigenvalues of those operators. Right. So I guess you are all familiar with that. Okay. Now F is the total spin, proton spin plus electron spin, and it can have two values, 1 or 0. So 1 means when proton spin and electron spins are aligned in the same direction. In that case, S dot I is h square by 4, and that is called triplet state because F is 1. So Z component of F will be 1, plus 1, 0, and minus 1. So these are degenerate states. So that's why it's called triplet state. When F is equal to 0, that means when spins are anti-aligned, they are in opposite direction, then S dot I is minus 3 by 4 h cut square. Okay. So this S dot I can have two values. One is h cut square by 4, and other one is minus 3 by 4 h cut square. So this interaction actually splits the ground state level into two energy levels, and that is shown here. So this is unperturbed energy level. But if you consider hyperfine splitting, that's the interaction between proton magnetic moment and electromagnetic moment, it splits into two states, singlet state and triplet state. Triplet because it has three degenerate states, and the difference between these two levels is of the order of energy difference between these two levels is of the order of 6 into 10 to the minus 6 electron volt. Okay. Uh, Now the corresponding frequency is 1420 megahertz. So that's how you can expect a transition with frequency of 1420 megahertz. Uh, so in order to get this number, actually you need to use on QED, quantum electrodynamics. But if you use this formula that I have shown, you will get 1422.8 megahertz. But in order to get more accurate value, you need to use quantum electrodynamics, which I am not going into. So I think this is clear. So 21 centimeter signal arises from the ground state neutral hydrogen atoms, and ground state splits into two states because of the interaction between proton magnetic moment and electron magnetic moment, and that gives rise to this radius. Okay, and if you want to know details about how we arrive this equation, there is a lecture available in YouTube by Somnath Bharadwaj. So there, this derivation is discussed. So you can actually go and look at it. I'm not going into that calculation. Okay. Now, why are we so concerned about hydrogen? Why we are interested in that hydrogen atom? See, uh, total out of 100, so total baryonic fraction in our universe, current universe, is 4%. And that is the component we can see. We cannot see dark matter, we don't know what is dark energy. So, but this is the component we can see and we can observe. So out of this 4%, 75% is in the form of hydrogen. So most of our visible universe is made of hydrogen, 3/4 of that, and 24% is helium, and the rest 1% is heavier elements that see all around us. Now, this 21 centimeter is a line emission. So actually, if we can observe this 21 centimeter line, and if it is coming from, let's say, redshift Z, it will be redshifted. The frequency will be redshifted to 1420 by 1 plus Z, right? So if we tune our observing frequency, we can actually observe any redshift between Z equal to 0 to Z equal to 200. I'm writing 200 because beyond that the signal is not observable, right? So, so you can actually probe each and every step of our universe evolution. So that's a great advantage. Second is that it is a probe of large scale structure of universe. So if you can observe neutral hydrogen, you can probe large scale structure of our universe, like scale of the order of 100 megaparsec or beyond that. And there are not many other probes which can actually do that. And also this signal, 21 centimeter signal, and the redshifted signal as well, can be observed from Earth's surface. So that is another advantage. So you don't need to go to space to observe the signal. You can build a radio telescope and observe this signal from the ground. And I think Saurabh will talk about that in more detail, how you observe and what are the challenges. But these are the advantages of using 21 centimeter signal in order to study our universe. Okay, so now I will stop the presentation and move to the blackboard and show you some calculations. Okay. So, so far I have discussed that there are two hyperfine states of ground state neutral hydrogen atom. One is triplet state and another one is singlet state. Now, let's assume that number density of hydrogen atom in triplet state is N1, and so this is number density of hydrogen atom in triplet state. And N0, the number density of hydrogen ground state hydrogen atom in singlet state. Okay. Now there are processes. There are three processes by which atom can go from singlet to triplet or triplet to singlet. There are three processes, and I will discuss those one by one. But before I discuss that, there is one characteristic temperature that is called spin temperature, and spin temperature is defined as N1 by N0, G1 by G0 e to the power minus H nu E by KB, KB Ts. So here Ts is the spin temperature. Lines. Is it okay now? It is? Okay. Okay. So this is how we define spin temperature. Assuming that this in triplet state levels, in singlet state levels are in equilibrium, we can write this ratio in terms of spin temperature. Now, G1 and G1 by G0 is around, it is actually 3, and G1 is the degeneracy parameter for the triplet state, G0 is the degeneracy parameter for the singlet state. Now you can immediately see that if spin temperature is extremely high, so this quantity, these are all constant, and you can calculate the number H nu by Kb, and that comes out to be H nu by Kb, that comes out to be 0.068 Kelvin. So very small number. Now, if spin temperature is much larger than that value, let's say 10 Kelvin, 100 Kelvin, or something like that, then this is very close to 0. Then this ratio would be G1 by G0, that is 3. That means 75% of ground state neutral hydrogen atom will be in the triplet state, and 25% will be in the singlet state. In case when spin temperature is very high, normally spin temperature is actually larger than this number. So on and around 75% atoms will be in the triplet state and 25% will be. Okay, and you can calculate spin temperature for a given ratio. Okay, so this number quantifies the level population ratio. Okay. Now, as I said, there are three processes by which this level population can change. So, let's say this is N1, N0, this is triplet state. And this is singlet. So what are the three processes by which atom can jump from this state to this state, or come from this state to. So one process is, the first one is a radiative transition. The first process is radiative transition. Radiative. So let's say you have radiation, background radiation corresponding to frequency 21 centimeter in the rest frame of these atoms. Then so this singlet state atom will absorb, it will absorb one 21 centimeter photon and go to that, it will go to triplet state, right? So so let's say we have this CMB background, and CMB has all kinds of photons, including 21 centimeter. So it will absorb 21 centimeter photons from this from CMB background, and it will go to the triplet state. And also it can, once it goes to triplet state, it can also decay, and there are processes called spontaneous decay. So if you keep one hydrogen atom in triplet state, and it will spontaneously decay into ground state, but that decay time is extremely small. So the decay rate, which is defined by, which can be calculated using Einstein's A10 coefficient, that is, the value of that is 2.85 10 to the power minus in second. So inverse of that will give you the average time of decay from triplet state to singlet state. So it is of the order of 10 to the power 7 years. Yes. Second inverse. Thank you. Yeah. So if you just calculate 1 by A10, the number will be around 10 to the power 7 years. So it will take 10 to the power 7 years for an atom to spontaneously decay from triplet to singlet. This is a large, long time. But then why it is so interesting? We have huge number of neutral hydrogen atoms in space. So although the decay rate is extremely small, we have some detectable signal. Okay, so it's not an issue that this decay rate is very small, because we have so much neutral hydrogen out there. So you can actually have some measurable signal. Okay, and apart from that, you have stimulated decay. Like if there is some 21 centimeter photon hitting this state, it can actually stimulate this atom to jump to the ground state. So those processes are there. So that is the first process, radiative coupling, radiative transition. Second is collisional. Collisional transition. So hydrogen atoms collide with each other. Hydrogen atom. So hydrogen atom is denoted. Neutral hydrogen atom is denoted as H1. So H1 atom, they collide with each other, or there can be collision between H1 or H1 electron. You have also free electron available in the medium during dark ages and cosmic dawn. So there will be collisions between H1 and free electron, or H1 and photon. So because of these collisions, atom actually can jump this state to this state, or it can also come down. Because see, this energy gap is very small. So even if the temperature is very small, eigenvalue temperature is very small, that collision actually is enough to collisionally excite singlet atom to the triplet atom, or vice versa. So that process is also important, collisional transition. And the third process is Lyman alpha transition. Now you may wonder how come Lyman alpha, which actually excites an atom from n equal to 1 to n equal to 2, actually helping to actually change the spin state. So I'll show you one diagram and then you will know how it's possible. So this is n equal, let's say it's n equal to 1 state, and you have two hyperfine states. This is triplet state, f equal to 1, and this is f equal to 0. And you have this n equal to 2 state. You have n equal to 2 state. Okay. Now you can also, there are some fine structure of this level as well, but I'm not going into the details. So you have this 2s, 2p, and then it will be further splitted. But now, now let's say one Lyman alpha photon hits this state, and if it is in this state, let's say in triplet state, it will go to n equal to 2 state, any of the 2p states, and it can come down to while coming down, it can end up in a singlet state. So it is indirectly changing the spin states, and then this, so this, and also this can also happen. Like it comes from singlet state, absorbs one Lyman alpha photon, goes to n equal to 2, and then while coming down, it can end up here. It can also end up in this state, but this is the one which actually, changes the spin states, right? So these are the three processes by which you can actually change the spin states. And once you change the spin states, you can actually changing the spin temperature, right? Now, okay. Now the thing is that all the process, each process like radiative transition, collisional transition, and Lyman alpha transition, they are in equilibrium. They are individually in equilibrium. Like if you consider radiative transition, that means in equilibrium, number of atoms, rate of change of singlet state atom is exactly equal to rate of change of triplet state atom. So number of atoms going from singlet state to triplet, and number of atoms coming from triplet to singlet state atom at some fixed time, they are same in equilibrium, and that is due to radiative process, and that is same for all three processes individually. So individually all processes are in equilibrium. Okay, so that is that we can assume, and we can write a balanced detailed equation. So we want to calculate. So let's say we want to calculate n0 dot. That means rate of change of singlet state atom number density, and that we can write as minus n0 T01 gamma T01 collision T01 Lyman alpha. Then N1 T10 gamma T10 T10. So what are these? So this quantity P01 is the rate of so this is the rate at which the singlet state atom is going to the triplet state atom. Per unit time. Okay, and due to radiative transition, and this is same for collisional transition, and this is for laminar transition. So P01 alpha, that means it is the rate at which singlet state atom is going to triplet state atom. Okay, and and this is proportional to the number density at the singlet state, and this is the rate at which triplet state atoms are going down to singlet state. Okay, so this P10 gamma, it is the rate at which triplet states atoms are coming down to singlet. Okay, now now so this is the amount which are going to the triplet state, and this is the amount which is coming down from the singlet triplet state, and that's how you can calculate the rate of change in the ground state, that is singlet state. Now in equilibrium, in equilibrium, this number is 0. These two processes they will balance each other. So the number going from down to up is same as number coming from top to the down. Okay, so this number will be 0, and not only that, each process like N0 minus N0 T01 gamma is equal to N10 P10, that is gamma. So this is they are same. Similarly, okay, so that is one. Okay, so we can write P01 gamma P10 gamma is equal to N1 by N0, and as we know that N1 by N0 is essentially G1 by G0 e to the power minus T H nu E by KB Ts. Now this quantity is written as T star, so I will write simply T star, but T star is H nu by KB. Okay. Now, as I also explained that T is normally much greater than T star. T star value is 0.068 Kelvin, and Ts normally it is much more than that. So we can assume this factor to be very small, T star by Ts to be very small. So e to the power minus let's say x, where x is very small, we can expand it. So that is G1 by G0 1 minus T star by Ts. So essentially P01 gamma by P10 gamma is G10 by G0 no, yes. Now, is it okay? Okay. Now, as I said, this each process will be individually in equilibrium. That means this characteristic temperature. So this is due to CMB radiation. This is radiative transfer. So this process is due to the CMB. This transition is occurring because of the background CMB radiation. Now that radiation temperature T CMB or T gamma, that will be equal to, it is in equilibrium, so the spin temperature will be equal to the T gamma. So spin temperature is equal to the T gamma, that is TC India, because they are in equilibrium. Okay, so we can actually replace this T gamma. Okay, now I am again explaining this. If there is no other process, only radiative coupling, radiative transition, then spin temperature will be exactly equal to the chamber temperature, and that's what I am written here. Okay. Now, similarly, when collisional coupling is the only process, in that case, I can write P01C by P10C is equal to G1 by G0 1 minus T star by T K, right? Because collisional process, the characteristic temperature is eigenvalue temperature. So so similarly, P01 gamma, sorry, collisional P10C is equal to D1 by D0 1 minus T star by TK, because characteristic temperature for collision is eigentemperature. Similarly, P01 Lyman alpha, P10 Lyman alpha is equal to D1 by D0 1 minus T star by T alpha or T color, alpha color temperature. So these are the three characteristics temperature when you consider each process individually. Okay. Now it has been actually shown that this alpha, T alpha or Lyman alpha color temperature is very close to the IGM temperature. So this color temperature, Lyman alpha color temperature, is very close to the IGM temperature. Why? Because hydrogen atoms are continuously absorbing and emitting Lyman alpha photons all the time, because it's a resonance transition. And because of that, Lyman alpha photon actually it is equilibrium with the motion of the hydrogen atoms. So that's why these two temperatures are very close to each other. Okay, so we can actually write T alpha same as Tk. Now, if I consider all three processes together, and as I said, all three processes are also in equilibrium, so we can actually write with 0. Okay, so essentially this quantity is equal to this quantity. So it basically tells you that number that is going up is same as number that is going down. That's it. Using all three processes relation that we have just
and then is it okay? I've just replaced this with the one that I just okay. Now you see we have this G1, G1 by G0 factor in all three terms. So we can actually cancel this. We can actually cancel this. We can cancel with this term. Okay. And see, we also have this P10 here, P10 gamma, P10 C, and P10 alpha. And also we have this similar term in the denominator. So we can actually write 1, the ratio of this term and that term. And then we have this second term. So second term is essentially, so it will be P star so let me write it here. So this will be first term is 1 minus so this is okay. So P star will is a common term, and then we have this first term is P gamma inverse, second term is P C inverse, third term is P alpha inverse multiplied by P10 gamma, P10 C, P10 alpha by P10 gamma. Okay. So now if you compare these two relations, you can really write P spin inverse is equal to this term. So basically, you can write this term PS inverse or 1 by PS is equal to basically this term. Is it okay? Or you are lost? I just compared the spin temperature that equation, so we can actually write this. Okay. Now we can actually divide numerator by P10 gamma, like we divide both in this term. So this term becomes 1. This term becomes P10 gamma and P10 gamma. Okay, and this is again 1, and this becomes P10 gamma, and this also becomes P10 gamma. So I have just divided by P10 gamma in both sides. Now you see we are actually reaching towards the very popular formula, famous formula. So PS inverse is P gamma inverse plus XC P TC, not TC, actually TK, is actually TK, TK inverse plus X alpha P alpha inverse plus 1 plus XC plus X alpha. So this is the formula that you always use to calculate spin temperature, right? This is the formula you will see in literature. So this is called collisional coupling coefficient, and this is called Lyman alpha coupling coefficient. Okay, and we can actually write that. So this is basically TS inverse, and we can write HC, the collisional coupling coefficient, to be P10C P10 gamma. X alpha is essentially P10 alpha by P10 gamma. Right? So this is called collisional coupling coefficient. This is also this Lyman alpha coupling coefficient. Now P10 can be further written as A10 P gamma by T star, right? So P10 P10 gamma. So this is P10 gamma. Okay, so P10 gamma can be written like this. So you can put this there, and you get the conditional coupling coefficient. Okay. Now see, in each modeling of Wilton cylinder signal, we need to calculate spin temperature. And spin temperature is a function of redshift, because T gamma is a function of redshift, Tk is also function. All these quantities are function of redshift. Also, it has spatial dependence. Like in each space, this number of redshift. So actually, people do simulation to actually simulate this spin temperature in the 3D box. But since my focus is on the global signal, basically we take a global average of this quantity. What is global average? So we will take a large space in the sky and then calculate spin temperature, average value of spin temperature for that particular sky or given base. So we will not calculate the specific fluctuation, but we will calculate the global one. And that we do for our purpose. But I guess this will show how to model this spin temperature. So there are various processes by which you can actually. So the important part to remember is that, particularly in the context of cosmic dawn, this thing, this X alpha modeling, it is one of the important part of this TS. Now, and XC, this collisional coupling coefficient, this is actually the quantity you can write. Let me write it. This collisional coupling coefficient. So this, I'm just again reminding you, this coupling is occurring because of the collisions between hydrogen atom or hydrogen electron or hydrogen proton. Okay. So that factor can be this K10, NH, P star, and K10. So this is something which that we can obtain literature. Then calculated level of K10. And so, for example, Zieglerman 2005, they are the table for this. So it depends on temperature. It depends on ideal temperature. So, yeah, so for various ideal temperature, the value is given in that table. This is number density of hydrogen. And we can easily calculate it from the cosmology. So this is your cosmology goes in there. This is constant, and A10 is also constant for this tension, and T gamma, the same temperature, which is also available. So using all these parameters, we can actually calculate Xc, that is a coupling, particular coupling coefficient for each dead C. These are all dead C dependent quantities, particularly image, this, and same temperature. So these quantities also dead C dependent. Okay, now tell me one important thing. So during dark ages, uh, there are no sources, as I said. So these parts will be actually zero. Since there is no line of photon, there is no line of particle. So these parts will be zero. So during dark ages, the formula will reduce. It will reduce to these parts only. So these part will not. This part will not be there. But for dark age, for the dark age, single. Okay. So you have to calculate for that. You have to calculate X horizontal coupling coefficient, and you can easily calculate. And identifier is also very well made. You don't need to consider contribution from sources, so that will be easy to calculate. So dark age Poisson signal, global Poisson signal can easily calculate. And uh, so we will see that this this Poisson coupling coefficient is very strong when temperature is very high. Ideal temperature, when ideal temperature, H1 kinetic temperature, when that is very high, this coupling coefficient is very high. And so during dark ages, this number is it is a reasonable number, like more than 1 for some red periods. And in that case, let's say X is very extremely large. If we assume Xc is much greater than 1, when the coupling coefficient is very strong, then tell me what is the value of free temperature in this equation? Just exclude this part. What is the value of free temperature when Xc is very large? Tk. So Ts will be equal to Tk. So it will actually so if I show you a plot, the very schematic diagram. So this is racing increasing, and this is someone that is signal. I have not defined the brightness temperature. This is delta T. No, so let's for the temperature. So CMP temperature is straight line, right? It is 1 plus L. And IBM temperature actually initially it is with the CMP temperature, but later it becomes. That is IBM temperature. This is PK, IBM temperature. Because it is due to elevated expansion, gas actually cools faster than the CMP. When they are not in, they are not up. But same temperature, if at higher exit, since this is very high number, X is very high. So same temperature will actually follow. It will actually follow ideal temperature. We have just seen, right? When X is very high, it will actually follow. Initially, it will follow ideal temperature. But later, this thing will actually it will become less than 1. Because why? Because ideal temperature is decreasing, and so also And also H1 density is also decreasing because inverse is expanding, so number density of hydrogen is also increasing. So there will be less collisions. That is, when you have less temperature, less density, collision will be less. So this factor actually becomes less than 1. So then if it is less than 1, then tell me what is the temperature of spin temperature? PCMBR. So actually it will catch CMBR temperature again. And that is the period called the dark age. So during dark age we have this, in some reaction range you have some spin temperature is regulated from the CMBR temperature. And we discuss why this is important. Because this will allow you to detect the signals. Okay. Any question so far? Yes.
So you talked about the Lyman alpha transition. So why doesn't the similar thing apply for Lyman beta or Lyman gamma and the other lines?
Yeah, so that I will discuss. You have to wait for that. So maybe today the second lecture I will discuss that. Because what happens that just to give answer briefly, Lyman beta also eventually converts into Lyman alpha. And I will show how. So all Lyman alpha Lyman series photons, Lyman beta, Lyman gamma, and higher photons, they will be absorbed by hydrogen atom, and some of will actually eventually become Lyman alpha. So ultimately, everything will be Lyman alpha. So that's why those are not important. Lyman beta, Lyman alpha. And yes.
So when will X alpha will be there in the graph?
Okay, so this becomes significant when there are sources, Lyman alpha sources, fast sources. So it is around 20. We don't know the exact number, but it is around 20. That is our target.
Yeah, so then what will happen to the spin temperature?
So then again, so due to Lyman alpha coupling, again it will couple. So this ideal temperature, it will again couple the spin temperature will again catch the ideal temperature. Okay, and then both will again rise because now you have these heating sources. So I will come all these processes one by one.
Sir, will the collision coefficient constant ever depend on the added hydrogen, like any strong or something?
Ideal hydrogen, so it will depend on, yes, so it depends, so this K10, it has contributions from hydrogen collision, hydrogen electron collision, and hydrogen proton collision. So ionized hydrogen means photons. Yeah, so it will also contribute, but mostly the dominant collision is hydrogen collision because they have so much of it, right? Inverse is fully mostly neutral, so you have more number of neutral hydrogen atoms compared to photons. So actually hydrogen collision dominates in this process, but of course they will also contribute this hydrogen proton collision.
Some calculations they use like there will NH, some people there will NH1 as well, so that makes the factor.
Plus NH1 that comes as because of neutral hydrogen collision. That is why they are. Because at high density, NH and NH1 is they are very similar, almost same. So you can actually replace NH by NH1. Yes, at redshift, I am talking about redshift more than 30. So universe is mostly neutral.
In that case, it's mostly.
So I think 1 hour is already passed, right? So shall I stop or I think Saurabh is waiting. So he'll talk about experience, global signal experience. So okay, so I will stop now and then I will continue from here to next last lecture. If you have any question, you can actually ask me. Why we need Lyman alpha, not other?
Why not partial bracket?
So the pattern gamma, so these are dimensions of let's say equal to 2 higher dimensions than any speed. So those are not useful for
Sir, I have a question.
yes.
So